All right, gang. I have thrown together a PowerPoint that is going to go step by step through the lab just to give you a better idea of how to go about answering the questions that you're responsible for the lab that's due this coming Wednesday, September 9th. But also keep in mind that you still have to get your Lab 2 discussions done and have two good experimental protocol proposals as the last response in your group thread on the discussion. So please do that, as well as this laboratory. This laboratory I find to be pretty fun. It's based on hormone axes. And if you don't know what that means, I'll go over it a little bit in this PowerPoint, but Chapter 6 covers it in depth. And of course, read the actual lab. This is instructions that are to supplement the lab handout that is the first document in the Lab 3 folder. So please open that up and read that carefully, as well as watching this video. The PowerPoints are very text heavy, and for the most part, I'm going to read off a lot of it and then add additional details or notes or suggestions along the way. Okay. I just named this "The Case of the Unknown Hormone Treatments," and why that title, why I chose that title will become clear once we get a little deeper into this this video. Okay, so the idea here is that you're looking at the results of an experiment that has already been conducted, and you're going to analyze some data from that experiment and come to some conclusions. And what the researchers did is they took a group of 14 rats. It's not a lot of rats, and if this were my experiment, there'd be many, many more so that we get good replication, right? I'm asking you to do 10, and these guys only did 14, and they're doing, what, 6 treatments here? I want 10 people for every 1 treatment you do, right? So this wouldn't hold up to the standard of our semester investigations, but that's not the point. The point is to get you thinking about how hormone axes work just in general, and using these specific examples to help drive that home. So the researcher or researchers, doesn't really matter. So a little team of researchers decide they want to do an experiment dealing with hormones, and they choose 6 different hormones: testosterone, luteinizing hormone, thyroid stimulating hormone, cortisol, thyroid releasing hormone, and adrenocorticotropic hormone. Okay, to do this lab properly, you're going to have to know what each of these hormones actually do, and I will not be covering that in this video. Okay, I will cover a little bit on a couple of hormones, but that's not the goal of the video. The goal of the video is to inform you and orient you to the task of completing this lab. Okay, all right, so those are the 6 treatments, and of course, if we have treatments, we need a control. Okay, and the control in this case is just untreated rats. Okay, so let me point that out. So they took, 7 terrariums, fish tanks. That's what people tend to keep rodents in. So there are 7 fish tanks, each with 2 rats in a tank. And I have a little diagram coming up here. Those 2 rats are different. They're both male, but one is intact. That is just a normal male rat, while the other male rat has been castrated. His testicles have been removed. Okay. And the reason for the testicles being removed is so we can better understand the effects on the male reproductive system of hormones like testosterone and luteinizing hormone, okay, which are male sex hormones. All right, so here are the treatments. So here's our 7 tanks. On the left by itself is the untreated control rats. And you see no syringe and no lettering because they don't get anything, okay? These are what you're going to compare these rats to, hence the control, all right? And you can see we got these 2 rats treated with testosterone. That's the castrated rat and the intact rat. Both get the same dosage of testosterone. Here's the luteinizing hormone treated rats. Here are the cortisol treated rats, the adrenocorticotropic hormone treated rats, the thyroid stimulating hormone treated rats, and the testosterone releasing, or I'm sorry, not testosterone, thyroid releasing hormone treated rats. So again, in each tank, there is 1 castrated male and 1 intact or uncastrated male. for lack of a better way of putting it. And so this was the original setup. So each of these tanks had a label that these rats got testosterone, these rats got luteinizing hormone, et cetera, et cetera. Okay, and that these rats did not get any treatment. These rats were set on a separate bench while these ones were set on a table, okay, with labels in this experiment. All right. And the plan for the experiment was that after the injections of the hormones, they were going to basically feed all the rats the same, keep them all in the same conditions. And then at the end of this, they were going to sacrifice these rats. That's the fancy way of saying killing them humanely. And then extracting the pituitary gland, the thyroid gland, the thymus gland, the adrenal gland, seminal vesicles, prostate, testicles, as well as taking the overall body weight. So they're first going to weigh these rats, right, one at a time, the control rats and all the treatment rats, and make a note of each of those, okay? And so they're going to weigh it before they take out the glands. Then they're going to open these critters up and excise the pituitary gland, dry it out and weigh it. Same for all the other structures on this list, okay? They're going to do that for the two control rats, and all 6 tanks with 2 rats apiece for all the 6 treatment setups, okay? So what were they going to do with this? Well, they want to see, what they're trying to drive as to see how hormone treatment affects these various tissues, whether it's the pituitary gland or the thyroid gland or the thymus, okay? So what they're going to do is they're going to, after killing these rats and weighing, or sacrificing, I should say, and weighing these organs, they're going to, what their job is after that is to compare the weights of these tissues in treated rats against the weights of those tissues in the control rats, okay? So my example here is we're going to take the control intact rat pituitary weight, and if you actually go to the handout sheet, you'll see that that is 12.9 milligrams, okay? And then they're going to take a treated rat pituitary weight, in this case I just made it up, it's 9.2 milligrams, and they're going to compare these two by basically taking the percentage difference between these two values. So how much did the hormone treated rat's pituitary weight change in that 2 weeks compared to the control? So how we do that is we're going to subtract the control weight from the treated weight for just the intact rat in this case. So control intact pituitary weight, treated intact pituitary weight minus control intact pituitary weight. We're going to divide that by the expected weight if the treatment did nothing, which is the control weight. And then to get the percent, we multiply that fraction by 100. So you're doing a simple percentage, okay? And if we always subtract the control weight from the treated weight, the sign of the percent change will indicate whether weight was lost or gained. And I'll go back through this when we get to the end of this video, okay? So the idea here is if I subtract the control rat's weight for the pituitary from the treated rat, if this is lower, we're going to end up with a negative value. And that's in fact what happens, right? We subtract 12.9 from 9.1 and we end up with negative 3.8 divided by the control weight times 100 equals negative 46%. So what this is saying is that the hormone treated rat lost 46% of its pituitary because of the hormone treatment it received, okay? And our threshold is going to be 19%. If it loses or gains 19% or more weight, we're going to say that that gain or loss is a real gain or loss, okay? Anything lower than that is likely just to be due to the different rats' weight before they started even, right? So those things, but if we have a big change, we can be sure that it's because of the treatment and not other effects that the rats might have came to the experiment having, okay? So that's your criteria, 19% or more of a change. Now that can be a loss, a negative change, or a gain, a positive change. So if this treated rat pituitary gland was 15.1 milligrams, then when we subtract, well, let's do it 15.9 to keep the math easy. If this was 15.9, we would subtract 12.9 from it, and it would be a 3 milligram gain, and whatever that is divided by 12.9, but it'll be a positive value. So your positive values will be gains in weight, negative values will be losses in weight. But if that negative value is 19% or greater, like 20%, 30%, then we have a significant loss. If it's greater than 19%, we have, or equal to or greater than 90%, we have a significant gain, okay? And that was their plan. But what happened? Late in the night, a custodian came in and removed the cards that were labeling all the tanks. And since the control rats were on a separate bench, the researchers knew the control rats were the control rats, but they didn't write down in their notebook, bad science, which tank got which hormone treatment of the 6 hormone treated tanks. They no longer know which tank got which treatment. And the whole goal of this lab is for you to use your understanding of hormone axes and some basic math skills to try to figure out which tank got which hormone, okay? That's the goal. All right. So how do we go about doing that? Well, first we got to understand how hormone axes work. And again, the laboratory that you can download actually goes into some detail on this, as well as your chapter 6 will have plenty of information about this as well. So please reference those if you don't find this video to be a good enough explanation for you. But I'm going to give you a good verbal explanation with this text here on the slides. Okay, so we're going to do testosterone. I'm actually going to do, at the end of this, I'm going to do group 1 for you. So I'm going to walk through group 1 as an example to help you work through group 2 through 6. Okay, all right. So for testosterone. So what do we know about testosterone? Well, the secretion of testosterone is actually not controlled entirely by the testicles. That's the gland that secretes testosterone, but how much testosterone it secretes, it makes and secretes, is actually regulated by 2 other glands, both basically on the brain. One is the hypothalamus, which is a brain region. The other is the anterior pituitary. That's the front lobe of the pituitary gland. These 2 actually regulate what happens at the testicle. This is also true of the ovaries. So the hypothalamus and the anterior pituitary also control ovaries in females, not just testicles in males. Okay. So how does that work? Well, the hypothalamus is connected by a stalk to the anterior pituitary. It secretes what's called gonadotropic releasing hormone. And that releasing hormone will travel from the hypothalamus down the stalk through the blood supply and then latch onto cells in the anterior pituitary. Those anterior pituitary cells will then secrete luteinizing hormone and follicle stimulating hormone, but we're not talking about that one. So we're just going to stick to luteinizing hormone. So GnRH secreted by the hypothalamus travels by way of the pituitary portal system. This is a couple of capillaries that are strung together, and in that capillary system of the anterior pituitary, gonadotropic releasing hormone is going to stimulate cells in the anterior pituitary to release luteinizing hormone, aka LH. Luteinizing hormone then enters the bloodstream and travels by way of the cardiovascular system to the testes. It travels to everything, but the tissues in the testes respond to luteinizing hormone. And what they'll do is when luteinizing hormone arrives, that stimulates a particular kind of cell called the Leydig cell. You don't have to remember that for this part of the class. That's way at the end in chapter 22. These Leydig cells will secrete testosterone that will then stimulate and regulate the production of sperm in the testes. And then also, as most people know from your sort of basic, street ideas of what testosterone does, is it's going to cause body weight gain, and it also causes the growth of male sexual organs, tissues like the prostate and seminal vesicles. Okay. Now, in addition to this pathway of getting testosterone to be secreted, these hormones have other effects. So be quiet, Jack. There's nobody here. Sorry, my dog is growling and I don't want him to make noise on the video. Stop it, buddy. Get back. Okay. So GnRH has pretty much a single job, and it's going to stimulate the anterior pituitary to release LH. LH, as I just said, goes to the testes and causes them to release testosterone. In addition to that, they enter the cardiovascular system, and when LH returns to the hypothalamus, it's going to inhibit the release of GnRH. So this is kind of cool. This is, as you learned from chapter 1, a negative feedback loop. So one job of testosterone is to positively affect the testes, or I'm sorry, one job of luteinizing hormone is to positively affect the testes, causing it to release testosterone, but also to negatively affect the hypothalamus to slow down the production of gonadotropic releasing hormone. So essentially, this prevents sort of a runaway production of GnRH by the hypothalamus, causing massive release of LH and then a massive release of testosterone. LH actually comes back to the hypothalamus and slows the production. And this is a self-regulatory loop. There's a set point. There's a certain amount of LH that the hypothalamus expects to be in the blood, and a certain amount of testosterone the hypothalamus expects to be in the blood. And when those hormones reach levels higher than that, they shut down or slow down the GnRH releasing process. This works very much the same way the thermostat works, as discussed in chapter 1. Okay? All right. Now, the testes, when LH arrives, are going to secrete testosterone. And of course, testosterone, as I said, goes to body, makes your body bigger. If you're doing a lot of working out, you'll be more muscular. You'll grow some muscle tissue, and your prostate will grow a bit, and your seminal vesicles will grow a bit. Sometimes testosterone also has a negative effect on the immune system. I don't know if this data bears that out, but it does happen. But it has another effect as well, and that is it's going to also feed back on the organs that control it. So it's going to negatively feed back on both the anterior pituitary and the hypothalamus, slowing the release of GnRH and LH respectively. Okay? Again, that's that negative, and that's how an axis works. The rule of thumb is that any forward gland is going to be stimulated by a previous gland, right? And any forward gland is going to inhibit any previous gland. All right, you might have to rewind that and re-listen to it. But that's the gist, and that's true of all of these hormone axes. You're looking at 3 different axes in this experiment. You're looking at the testosterone axis, you're looking at the cortisol axis, and you're looking at the thyroid hormone axis, okay? Just off the top of my head, the job of thyroid hormone is to regulate metabolism. When you have lots of thyroid hormone, you're going to burn a lot more calories and you're going to tend to lose weight when you have high thyroid hormone levels. Cortisol is a long-term stress hormone. Its effects are to simultaneously suppress the immune system. So you should expect, shrinkages in glands that are dealing with immune function, like the thymus gland. And it also mobilizes your energy stores. So like thyroid hormone, you will find that cortisol will cause weight loss. So you're going to suppress the immune system. With high levels of cortisol, your immune system is going to be suppressed, and you're going to have some wasting. You're going to lose some weight. So those are the main body effects that those axes are trying to regulate. Okay. Okay, so what does this mean about glandular weight? So if I inject a rat with a hormone, any structures that stimulates are going to become larger. They're going to gain weight because you're putting them into overdrive by adding additional hormone. So what does that mean? If I inject a rat with testosterone, and this is an intact rat that still has its testicles that are already producing testosterone, a number of things are likely to happen. One is that you're going to hyperstimulate all of the things that testosterone would normally stimulate, which is what? Body growth and sexual reproductive growth. So we should see an increase in the mass of seminal vesicles, increase in overall body mass, and likely an increase in prostate mass if we add additional testosterone, right? Okay. But what should it also do? Well, if you put testosterone in, the very gland, the testicle that's supposed to secrete the testosterone, doesn't have to work as hard anymore because you're supplementing what it would normally have to do plus some. So what will happen is the testicles will begin to atrophy and shrink. They'll become less massive. And people that are on heavy, heavy duty testosterone, like bodybuilders and such, it's not uncommon if they stay on testosterone for a long time without cycling it, that their testicles shrink to the size of raisins, literally. That's not an exaggeration. Okay, so when you inject a hormone, the gland that's supposed to produce that hormone usually atrophies, becomes smaller, and loses weight. Okay. Also, any glands that come before that gland in the axis chain will be it'll be hyper inhibited. So if I inject the rat with a boatload of testosterone, we know that that's going to inhibit the hypothalamus, and it's going to inhibit the anterior pituitary. And that abnormal amount of inhibition may cause those structures to shrink as well because they're not producing their normal amounts of LH and GnRH, respectively. Okay, so these are what we should expect. This is how we should expect weights to change based on hormone treatments. Okay. All right. So if you go to your lab, you're going to find that you have basically one control group and 6 treatment groups. In each group, as I discussed in the front end of this video, has an intact rat and a castrated rat. Make sure when you're comparing the weights of organs that you only compare the intact treatment rat to the intact control rat, and the castrated treatment rat to the castrated intact rat. Okay, you need to be apples to apples, not apples to oranges. All right, and you're going to go through and do this for each group. And if you see a gain or a loss of 19% or more in any of the structures, you need to record that, because the goal of the lab is to figure out which group got which hormone. And the way you figure that out is looking at which structures grew and what structures shrunk. And the pattern of shrinkage and growth should clue you in as to what hormone was the likely culprit or the likely treatment. Okay, so let me give you an example for rat 1. Not rat 1, group 1 of 2 rats. Okay, so don't ignore the text for now and just look at these panels. Okay, I set up a little Excel spreadsheet to save me a lot of mathematics. Okay, so I put the control rat here, and you see that it says control intact rat, and I'm going to compare that to group 1 intact rat that had some so far unknown treatment, because remember, the labels were removed from the tanks. Okay, so you go to your sheets and you look at the control rat. For intact, you'll see that all these values that I've put into this spreadsheet are the same as the intact control rat. Okay. Next to that, I put the group 1 intact rat, and you'll see that there's some differences here. Okay. So I calculated the percent differences. If we go from 12.9 to 12.8, that's a loss of weight, right? Control rat is 0.9, intact rat is 0.8. That's a tenth of a milligram loss, because these are in milligrams, except for weight, which is in grams. Doesn't really matter because you're calculating percentages. So that turns out, if you do the math, to be a negative 0.78% loss. So a 0.78% negative value means a loss of 0.78%. So that's the percent change or loss. That's not 19% or greater, so I didn't put anything there. Okay. I did it again for the thyroid. Here we got a 5 milligram loss. If we do 5 milligrams divided a loss, negative 5 milligrams divided by 250 times 100, that'll give us a negative 2%, also not 19% or greater, right? So again, I leave that blank. Now we see here we go from 475 in the control to a really low 150, you can eyeball this and know that that is more than a 20% loss, right? That's more than 100% loss. If this thing had lost, what's half of this? Half of 275, or 475 is 237-ish. If this was 237, it would be a 50% loss, okay? It's more than, I'm sorry, more than a 50%. 100% loss would be zero, right? We would have to lose all 475 milligrams. But we've lost more than half. And that's borne out. When I do the actual calculation, I can see that it's a negative 68.42% or a 68% loss. So that's significant. That's more than 19%. So I put a negative there. So that's a loss. Also a loss, or actually here we see an adrenal gland gain, right? The control has 40 milligram adrenal gland. Here you see 100 milligram adrenal gland in the intact treatment rat for group 1. That's a massive gain. It's more than 100% gain. 100% gain would be 80, right? We would double this. We more than double it, so we get 150% gain. So I put a plus there because that's 19% or greater change, okay? So for seminal vesicles and prostate and testes, we see there is a change, but it's very small, so we can ignore it, right? And then finally, we see body weight drops 100 milligrams, so a full third of the weight is lost. A third is 33.3 repeating percent, so that's a negative sign, okay? And you're gonna look at this pattern. All of this business here is just to get to see which glands have gained or lost, so you can try to figure out which hormone treatment this group got, okay? So now let's look at the castrated rat. Group 1 castrated rat, no change in pituitary, no change in thyroid. Once again, a huge change in thymus, very similar to the intact group, right? Intact rat. Here we see another massive gain in adrenal gland mass. Here we see a bit of a loss in seminal vesicle, okay? And then, it's a loss. We got to put a negative there because it's 19% or greater. And then finally, we see a similar body weight loss, okay? Now, let's look and say, just look at the first one and say, okay, which gland is being affected here? Well, the thymus, but none of the hormones we're looking at are secreted by the thymus gland. In fact, the thymus gland doesn't secretes what are called leukotrienes, and these actually help the development of immune cells, your T cells and B cells. So none of the hormones that the 6 hormones we're concerned about are secreted by the thymus, okay? What about the adrenals? Oh yeah, the adrenals are affected by 2 different hormones that we're looking at, ACTH and cortisol. Those are 2 of the treatment hormones that we know were injected into some rats, okay? So that narrows it down. Now we just look at whether or not an injection of ACTH or an injection of cortisol would produce this pattern that we see here in losses and gains. Okay, so let's look at cortisol. Cortisol is what the adrenal glands secrete, okay? And we know that if we replace a hormone that a gland secretes, that gland will shrink in response because it won't have to do as much work because you're injecting that same hormone from the outside. But what do we see? We actually see the adrenals are growing. Well, that's not consistent with cortisol, or that's not consistent with cortisol injections, right? Cortisol injections should cause the adrenals to shrink because the adrenals produce cortisol and you're replacing what it would normally secrete. All right. However, the negative here and the negative here are consistent with cortisol secretion. So if there's lots of cortisol, right, we should expect body weight loss and immune suppression, okay? But we wouldn't expect cortisol injections to lead to a growth in the adrenal gland. So our only other culprit is adrenocorticotropic hormone, which is secreted by the anterior pituitary. And what's its job? Its job is to stimulate the adrenal glands to produce cortisol. Okay, so now I'm going to jam this rat full of ACTH, and it's going to cause the adrenal glands to work overtime and overproduce cortisol. And the process of overproducing requires the building of infrastructure to make more cortisol, which causes tissue growth and increase in mass, increase in weight. So ACTH is consistent because it would cause the adrenal glands to grow because of the production of more cortisol, and the cortisol would really lead to the shrinking in the thymus and the loss of body weight. Okay. And we see that the pattern's more or less similar in both castrated and intact rats, aside from this weird thing with the seminal vesicles. This is kind of an outlier. This isn't really explained by ACTH, but sometimes we see things happen that are a little weird. If you go through and you try to find out if testosterone or luteinizing hormone would have these effects, you'll find that they actually don't. Luteinizing hormone will not affect the size of the adrenal glands, and certainly not by 137%. So this is some kind of weird effect of the experiment, which happens all the time, okay? So really, we're pretty sure that this pattern of weight changes in these glands, these tissues that were measured, are consistent with ACTH more so than any of the other possible any of the other 5 remaining possible hormones. Okay, so hopefully that is enough to get you through to working on your groups 2, 3, 4, 5, and 6. Okay, and then once you get those, you're going to answer the question sheet and submit that in the lab 2 or the lab 3, I'm sorry, folder in the content area. Okay. So I hope this was helpful. If you have any further questions, of course, consult your book, consult the actual lab that's in the folder, and then email me or come to my office hours, right? They're on the syllabus. Um, I am there with WebEx open, just waiting for people to come in and talk to me. So hopefully I will see you there either for this or something else.